Yeah, 28.
Hello, how you going? Today we're going to be covering the Formula Society of Automotive Engineers Electric Vehicle Team. My name is Ryan Miller, and with me is Raphael, Ann, Gary, Ethan, Slavin, Ben, Spencer, and Branson. And our faculty advisor for this project is Dr. Farisad. The objective of this project is to design, test, deliver an electric vehicle that places among the top times from the 2019 FSAE competition.
Our primary customer is the LSU Tiger Racing Team, since they will be transitioning into electric vehicle competitions in the future. A second consideration was given to the FSAE judges, since they will be scoring the vehicle at competitions. For our competition, we looked at universities that placed among the top 5 positions at events. This included the University of Wisconsin and MIT. To improve on their designs, we improved the power to weight ratio by optimizing the power output of the battery and designed our own battery management system to cut cost.
We had 3 functional requirements for this project. We were to create a vehicle that moves under its own electric power, be competitive at FSA competitions, and document the design of each of our subsystems so the Tiger Racing team could use our design moving forward. We also had 5 qualitative constraints for this project. We had to meet the FSA safety requirements as well as follow the legal specifications for FSA competitions. We had to complete the project within budget, create a vehicle that's easily maintained, and we also had to use the 2018 Tiger Racing chassis.
These are our wide array of measurable engineering specifications. Some include a distance per full charge of 25 kilometers in order to complete the endurance event, a 75-meter acceleration event in 4.5 seconds, a skid pad event in 5.5 seconds, and a mass of 250 kilograms. This is our functional objective tree, which includes cost, safety, performance, ease of use, and efficiency.
The project was split between the mechanical and electrical systems. The mechanical system consists of a drivetrain, cooling, and battery housing subsystems, while the electrical system consists of a battery pack, motor, motor controller, auxiliary, and battery management subsystems. For the battery pack, we looked at 3 common battery chemistries used in electric vehicles today, which are nickel metal hydride, lithium ion, and lead acid. Through a normalized pairwise comparison, we determined the weights of each criteria. The most important criteria for battery chemistry are weight and energy density. A normalized decision matrix was then used to determine that lithium ion would be the best battery chemistry because of its low weight, high energy density, and availability within the market. Let it be known that all component decisions within our project utilize strength and weakness analysis as well as decision matrices to determine the best option for our vehicle. We then compared the 18650, 21700 cylindrical cell sizes and determined that the Samsung 18650 cell would be the best option because of its high energy density, low weight, and low cost. Here's a representation of our battery pack design. It is a 4.4 kilowatt hour pack consisting of 448 cylindrical cells. The pack is configured in a 28 series 16 parallel configuration. The individual cells are fused on both terminal ends to the copper bus bars by 23 gauge copper wire so that the cell disconnects from the battery pack if a short or large spike in current occurs. This fuse protection, along with the battery management system, is essential for the safety of the vehicle and driver. In total, the pack will produce 170 volts max and be able to output approximately 500 amps to the motor. We then simulated the current discharge of the entire battery pack within Simulink according to the specific parameters given within the cell's datasheet. The top graph is a representation of the nominal current discharge of the pack at 160 amps, and the bottom graph represents various loads. The red line is a representation of the average simulated load of 170 amps that the endurance event will require, while the purple line represents a max full throttle 500 amp load. To determine the average simulated load from the endurance event, we utilized Optimum Lab software in order to simulate our vehicle with the exact battery type, motor, and force parameters. A single lap simulation was then performed on the 2019 Lincoln Endurance course in order to determine how much energy was spent. From the data given, our vehicle will use approximately 1.45 megajoules per lap, which equates to the vehicle discharging an average of 170 amps throughout the endurance event. For testing of the battery cells, we had to ensure that no cell was considered defective. A cell is considered defective if it has a capacity significantly less than 2,500 milliamp hours, an internal resistance significantly less than 18 milliohms, or is not able to hold its full charge for an extended period of time. Defective cells have a higher probability of exploding due to the chemicals internally heating up and igniting at temperatures above 1,000 degrees Fahrenheit. To test the capacity of each cell, we ran a NOR test on each one using smart chargers, which discharged the cells to 2.5 volts and then charged them back up to the full charge of 4.2 volts. We then were in the process of leaving the cells fully charged for 2 weeks in order to ensure that each cell could hold its full charge properly. Lastly, we were in the process of calculating the internal resistance of each cell by utilizing Ohm's law and comparing the values with a datasheet. If any cell was considered defective from any of these three tests, the cell would have not been used in our battery pack design.
The motor and motor controller are referred to as the motor system. We originally had the MRAX 228 motor in our design at the beginning of the semester, but due to budget reasons, we cut the battery pack down and was forced to get a smaller motor. We decided to go with the MRAX 208 low voltage air-cooled motor. Due to COVID-19, we were unable to order and receive the DTI HV500 motor controller and the MRAX 208 motor. Therefore, we were unable to run tests on the motor. However, we were able to run analysis on the performance. So the torque and speed required to meet our vehicle acceleration specs were 108 newton meters and 5,600 RPMs. The MRAX 208 motor specifications are 140 newton meters at max torque, 6,000 RPM at max speed, and 68 kilowatts at max power.
To estimate the motor's required torque, we looked at the major forces on the vehicle, which includes the force required to accelerate the mass of the vehicle, the rolling resistance, and the air drag on the vehicle. Then by multiplying this tractive force by the 8-inch radius of the wheel and adding the torque required to accelerate the four wheels, the driving torque could be found. Then a series of plausible gear ratios were multiplied to this value in order to find a smaller, lighter motor that could achieve this torque.
Once we calculated our necessary motor outputs, we simulated the isolated motor to observe its behavioral characteristics. We used a simulating structure to model our drive that replicates that of that MRAX 208 low voltage and the DTI controller we would have purchased. From the Simulink model, we observed a continuous mechanical power output of 38 kilowatts, continuous torque of 60 newton meters, and a rotor speed range of 0 to 6,500 RPM. All these parameters coincide with the ones listed on the datasheet for the MRAX and show that our motor selection would have been enough to satisfy our project's performance needs. After we confirmed the motor operates properly by itself, we simulated the motor performance when connected to our gear ratios. With the gear ratio, we're able to achieve a peak torque in our acceleration event and a reduced continuous torque when our vehicle approaches its top speed. These allow us to achieve our acceleration performance analysis using Optimum Lap software.
Using the Optimum Lap software, we ran a full vehicle simulation of an endurance course and the 75-meter acceleration event. Putting in the parameters of our car resulted in an endurance time of 85.57 seconds and 75-meter event of 4.59 seconds. These results would have placed us 4th overall in acceleration and 1st overall for endurance.
The auxiliary systems are made up of the sensors, devices, and controllers that provide system feedback and control, as well as ensure the safety of the vehicle. The brake pedal position sensor and accelerator pedal position sensor accept input from the driver and relay the equivalent torque request to the motor controller inverter. The Arduino also takes the sensor output to monitor for faults and sends a signal to the battery management system if one occurs. Additionally, the Arduino controls auxiliary devices like the brake light and cooling fans. The brake system plausibility device, or BSPD, monitors the pedal sensors and other systems for faults through analog means required by the FSAE rules. The BSPD is in series with 9 other safety devices that make up the shutdown circuit, shown by the red connections. If a fault is detected by any of these, then the circuit opens and cuts power to the high voltage battery pack. The BSPD monitors all the pedal sensor outputs for open or short circuit faults. Also, it uses the high voltage battery current sensor to measure the power delivered to the motor. It registers a fault if more than 5 kW is delivered to the motor while the driver is braking hard. The NAND gate senses for the low fault signals and outputs a high signal to the RC timer if one occurs, allowing it to charge. If the RC timer charges for 500 milliseconds, then the normally closed relay in series with the shutdown circuit opens.
The first step in testing the BSPD circuitry was to build the brake and throttle fault detection section of the circuit on breadboards using the schematics as reference. To ensure that the circuit was working properly, we used a voltage source to power and simulate signals to the logic of the circuit and a multimeter to measure the output. We compared the outputs to the expected output values to confirm proper functionality. We ran 3 tests on the 4 sensors output detectors. First, we sent different signals between 0 and 0.5 volts to ensure we received a low signal of 0 volts, or that we detected a short circuit fault in the sensor. Second, we sent different signals between 0.5 and 4.5 volts to ensure we received a high signal of 5 volts, or that we registered no fault to the NAND gate during proper functionality. Third, we sent 4.5 to 5 volts to ensure we received a low signal of 0 volts or that we detected an open circuit fault in the sensor. All 4 brake and throttle fault detection circuits passed every test. We use the same equipment and methods to test the motor power during hard braking fault circuit, except that we added a second power supply since we simulated signals for 2 sensors. We performed 4 tests using 0 to 4 volt signals to simulate no hard braking, 4.1 to 4.5 volt to simulate hard braking, 0 to 2.35 volt to simulate motor power under the 5 kilowatt limit, and 2.35 volts to 5 volts to simulate motor power over the limit. All tests were a success and outputted the correct high and low signals respectively.
The integration test, we used 2 power supplies to simulate fault scenarios and an oscilloscope to measure the RC timer output. We use this test to ensure that the circuit measures a fault for 500 milliseconds before opening the relay to the shutdown circuit. We performed 3 tests with different fault scenarios. First, we simulated no fault signals from eddy pedal sensors or the hard braking motor power sections. As expected, the NAND gate output was a low signal and did not allow the RC timer to charge, leaving the relay closed. Next, we simulated all the fault signals in turn, and the NAND gate output was high, allowing the RC timer, shown by the yellow line, to exponentially charge and trip the relay, shown by the blue line, after 500 milliseconds. Third, we simulated all the fault signals at once, and the NAND gate output was high, allowing the RC timer to exponentially charge and trip the relay.
The auxiliary systems integration test evaluated the functionality of our control Arduino and its accessories. Once the program was uploaded to the microcontroller and the power was initiated, we were able to validate that the 4 cooling fans turned on, the brake light turned on when the brake sensor was actuated, and that no fault was activated feeding to our shutdown circuitry. In this photo, we can see the DC power supply acting as our vehicle's 12-volt battery, the microcontroller running our control program, the 4 cooling fans that would have been mounted to our battery pack, mounted on the rear of the vehicle as our brake light, and the accelerator and brake sensors. For the Arduino code, the microcontroller is turned on or off depending on if the ground low voltage system is activated. The microcontroller reads the 2 analog signals from the 2 brake and 2 accelerator sensors and calculates the voltage of each sensor. FSAE mandates 2 sensors for brake and 2 for accelerator for increased safety when operating the vehicle. If the percent difference between the 2 brake and the 2 accelerator sensors are greater than 10%, a fault is sent to the battery management system. Additionally, if the acceleration pedal is pushed more than 25% and the brake pedal is actuated at all, another fault will be sent to the BMS. If either fault is sent, the high voltage circuit disconnects the battery pack with the shutdown circuitry and turns off the vehicle immediately.
The battery management system, or BMS, is responsible for monitoring the voltage and temperature of the battery pack. If either gets outside the provided operating limits, then power from the battery pack will be disconnected by opening accumulator isolation relays, or AIRs. The TEVA TM4C series microcontroller was selected for the processing due to its low cost and ease of use, and was programmed using C with the TI Code Composer Studio.
We used integrated circuits in the BMS to monitor the temperature and voltage of our battery cells. For this, we chose the BQ79606A due to its low cost and high measurement accuracy. We also decided that the master-slave topology was the best for our project due to its low cost and ease of maintenance. Here we have the wiring diagram showing the interconnections between the BMS and the rest of the vehicle. We can see that the BMS is made up of a master board and 5 slave boards shown in the red boxes. The slave boards take the voltage and temperature measurements of the battery pack and communicate that information to the master board via UART, a communication signal. The master board, which contains the TEVA microcontroller, then processes this data and controls the errors based on the results. If the measurements are within an acceptable range, the microcontroller allows the errors to connect to ground, therefore allowing power to flow to the rest of the vehicle. If any of our safety conditions are not met, the microcontroller leaves the errors open, disconnecting the battery pack from the rest of the components.
So the first step in the BMS program is to initialize the microcontroller and IC pins. Next, an initial voltage and temperature measurement is taken to ensure that the battery pack is within operating limits before any of the errors close. If the driver wants to enter the drive mode, they must press the ignition button while holding their foot on the brake. This will initiate the pre-charge sequence for the errors, which allows for the motor controller to charge up to 117 volts over 3 seconds, preventing any large inrush current. After this, the program begins to monitor the voltage and temperature of the battery pack. If the user wants to charge the battery pack, they must select the charge mode, which closes both the airs, then begins monitoring the voltage and temperature. In both BMS modes, the program is checking for 5 consecutive halts to ensure no error in readings before opening the airs. In order to reset the program, the reset button must be pressed. Using MATLAB, we were able to calculate the required pre-charge resistor value to achieve a pre-charge time of 3 seconds. Since FSA rules require the motor controller to be pre-charged to 90% of the battery pack voltage, 3 time constants are needed for the calculation. Using this value in the internal capacitance of the motor controller, we found that in order to pre-charge the motor controller in 3 seconds, a resistor value of 5 kiloohms is needed.
In order to ensure the proper functionality of our microcontroller, we first tested the GPIO pin outputs. We did this by connecting LEDs to the GPIO pins that will control our airs and observing whether the LEDs light up when we run our test program. Here we can see the results of the GPIO output test. In the picture on the left, we can see that in the first section of our code, the LEDs connected to the pre-charge and negative terminal GPIO pins are lit up. Then, after 3 seconds, the pre-charge LED turns off and the positive terminal LED turns on, verifying the GPIO pins are outputting correctly. The next test we performed was the microcontroller MOSFET/relay control test. For this, we connected a 12-volt battery to the coil of the relay, which causes the contactor to close. We then connected our microcontroller GPIO pins to the in MOSFETs that will control the grounds of the airs. When the in MOSFETs are on, they will connect the airs to ground, allowing power to flow across the relay to an LED. Here we can see that the in MOSFET is turned on by the microcontroller, which grounds the air. The air contactor then closes, allowing power to flow to the LED, causing it to turn on. This test was a success and verifies the functionality of our shutdown circuit.
In order to determine if the microcontroller was sending the correct UART transmission, a test was done using a sample UART function from the BMS program and was analyzed on a network analyzer. By viewing the bit stream that we hoped to send, we could determine whether the microcontroller was transmitting correctly. Using the bit stream shown, we were able to view the output response on channel 1. Since the UART protocol being used is 8-N-1, there should be a start bit of 0 and a stop bit of 1 after each byte of data that is sent. Viewing the output, we can see that the correct bit stream was transmitted, making this test a success. After confirming the microcontroller was transmitting correctly, we moved on to testing the communication between the IC and microcontroller. For this test, we connected one IC to the microcontroller, then connected the IC to a single battery cell. We hope to be able to print out the measured voltage of the cell in the terminal window. So after configuring the setup shown, we were unable to receive any signal back from the IC. We had originally planned to use the IC breakout board that is shown to test communications, but after contacting TI, they informed us that all the supporting circuitry surrounding the IC was required, and since we were not able to ship our slave boards off to be soldered, we were unable to test any further.
To integrate the motor to the wheels, we chose to use a Drexler V3 differential for its adjustability and low cost. This visual shows the modifications required to mount the battery housing and the motor to the existing 2018 frame. A simulation was run to determine if the frame would fail under a 40G crash scenario. Using the weights of the battery housing and motor with attachments, it was found that the peak stress was 323 megapascals, which is less than the yield strength of chromoly 4130 steel of 460 megapascals.
The battery housing will hold and protect the battery pack and low voltage system. We decided to mount a removable compartment to the rear of the vehicle using decision matrices considering cost, weight, and safety. The final iteration of the battery housing design is shown here with 4 battery pack sections and a total of 10 attachment points. The number of attachment points and weight of all the components in the battery housing were known. We were able to estimate the shear and bearing stresses on the attachment points. The bearing stress of 89 megapascals was used as a minimal requirement for the material selection process. This is shown by the horizontal line in the Ashby chart to the right. The diagonal lines were made to show options for the design of a light, strong panel. Aluminum alloys were among the strongest candidates here. We looked at a few more charts to find our best options. The chart on the left considers the design of a cheap, strong panel, where carbon steels perform slightly better than aluminum. However, we finalized our decision on aluminum by taking its thermal conductivity into account, as shown on the right side. The image shows a simple fault tree with our predictions of what could cause a structural failure in the battery housing. We decided to conduct impact tests on the welds to test our welding procedure and quality. Additional static and frequency finite element analysis was conducted in lieu of testing the finished product. Here's a testing document for the fracture toughness test. The test involves measuring the energy absorbed by a material before fracture using a Charpy V-notch testing setup. Some test specimens were manufactured out of the base material as a reference, while others were cut in half and welded back together to test the toughness of the welds. Unfortunately, there were some issues with the manufacture of the welded test specimens, and we were unable to get accurate results before on-campus facilities shut down. The two first images show the results of the welded specimen and the base specimen respectively. The results for the welded specimens averaged around 3 joules of energy absorption, when the base specimen had around 30 joules. The left side of the last picture shows the fracture surfaces of the welded pieces, which shows the weld did not fully penetrate the material, which is a clue as to why the results were so low. A plan was made to machine the test specimens out of a long, welded section of material, but it could not be completed because of closures due to COVID-19. Further, FEA was conducted on the battery housing as a replacement for some of the real testing that could not take place. FSAE rules specify that the battery housing attachments must be able to withstand a load due to an acceleration of 40 Gs in all horizontal directions and 20 Gs vertically. This shows a simplified model around one of the attachment points, which resulted in a 155 peak stress for forward and aft directions, leading to a factor of safety of 1.2 at the weld. The attachment was able to withstand the loading conditions in every direction as shown in the following images. More in-depth analysis can be found in the appendix.
For the battery cooling system, we decided to use a forced air convection system due to its lower cost and high heat transfer rate. To determine the heat generated by the battery pack, we first had to determine the specs of the pack. This was done by using the specs of 448 individual 18650 cells in series and parallel. Then the joule heating was calculated for the two most demanding competition events, the acceleration and endurance event. As you can see, the heat generated during the acceleration event is much higher, but the time of the event is very small. Therefore, we decided to design the cooling with respect to the endurance event, which is substantially longer. With an ambient temperature of 40 degrees Celsius, the battery will finish the event at 85 degrees Celsius. This picture shows a rough diagram of the ambient air being drawn through the cells and a square duct added to the bottom of the housing by two PC fans. With this design and a volumetric flow of 0.1 cubic meters per second produced by the fans, the change in temperature is reduced to 33 degrees Celsius, which brings the final temperature to 73 degrees Celsius.
The picture on the left shows the 2018 chassis as we received it from the Tiger Racing team. We assembled the uprights and hubs with new bearings and mounted the wheels and suspension. The picture on the right shows the assembled systems. In efforts of getting a rolling chassis before the EV systems were integrated, we had to manufacture a steering system. We used the 2014 car steering rack and welded a new steering column mount.
For electrical manufacturing, we were able to manufacture the BMS slave PCBs, the battery stack, and the Arduino PCB.
Our safety considerations were largely focused by the FSAE rulebook, which dictated most of the safety parameters of our vehicle, such as the shutdown circuitry on both high and low voltage systems, the presence of a firewall between the driver and motor, and the 40G force requirements on the structural components. Additionally, our larger components have ingress protection ratings, making them dust and water resistant.
A few of our safety considerations during the manufacturing and testing phase included the proper use of PPE, implementing a 6-point driving harness in the vehicle, ensuring all safety circuits are functioning properly before the vehicle is tested, and having an ABC fire extinguisher located nearby.
For the environmental impact assessment, we significantly reduce emissions during operation, being an electric vehicle. However, there are upstream greenhouse gas emissions from electricity production plants such as coal. The lithium-ion batteries we are utilizing in our battery pack are easier to recycle than most other battery types because they are less toxic. All of the metal used on the chassis as well is recyclable.
We were given a budget of $15,000 for this project. Before the semester was cut short, we were projected to spend $11,922 to complete our vehicle, which is under budget, shown on the left. However, we actually only spent $4,544, with the majority of that money being spent on our battery pack and our auxiliary systems.
For our project timelines, we show our predicted milestones in yellow and the day they were actually realized in purple. Our purchasing schedule was first delayed by vehicle redesigns caused by budgeting issues in the beginning of the semester. So we purchased the parts not dependent on the motor and battery pack redesigns and proceeded as much as we could with those subsystems. Our motor purchase order was delayed again because of international purchasing issues, and the gray line shows the date that the COVID-19 school closures halted our progress. We proceeded with battery management and auxiliary system testing in the beginning of the semester, but testing for other systems was delayed by the purchase order issues with the motor. We were able to complete some subsystem and material testing before the COVID-19 closure date, shown in gray. Despite the motor ordering issues and multiple battery pack and battery housing redesigns, we were on track to finish the vehicle by our internal April 9th deadline before the COVID-19 closure stopped our progress. We could have saved valuable time by better communicating with faculty and our sponsors earlier in the project to completely understand our scope, budget, and purchasing requirements. Misunderstanding these things caused multiple redesigns to the motor, cooling system, battery pack, and battery housing, as well as delaying the purchase of the materials.
Here we have the final assembly of our vehicle, highlighting the electric powertrain and frame modifications that we designed this year. And we now want to open the floor up to any questions.
All right. Thank you for the presentation. Do we have any questions? Richard? Richard?
Yeah, I'm here. I had to find the unmute button. One question I have, you showed your little computer cooling fans pulling the air through your battery packs.
Yes,
What
sir.
kind of air temperature do you think you're going to get through those, and how will that affect the fans?
As of right now, we're expecting temperatures of around the final temperature of the battery cells, but we didn't do an in-depth analysis of exactly how much temperature the air changes.
Well, I mean, what are the fans rated for?
I don't know that value.
Because the fan doesn't care which way it's moving the air.
Yes, sir.
You put it on the cold side, you'll actually probably move more air because it's pushing denser air.
Okay. I'll take that into consideration. We read articles stating that those PC fans are usually used to draw air, and it's more efficient to draw heated air, but we can look into it further.
Well, it is, but the fan has to be, built that it can handle the high temperature air.
Yes, sir.
I don't know that little computer fans will stand up to, the temperatures you're talking about for very long.
Yes, sir.
All right, I'll give it to somebody else.
So the question is there anybody else? Yes, we have Nikita Pitts. Nikita, please go ahead.
Hello. I was just curious what software you guys use for the FEA analysis. I'm not sure if I missed what you guys use.
We used ANSYS.
We used ANSYS and SolidWorks.
SolidWorks as well, yes.
SolidWorks as well.
Okay, that was all. Thank you.
Speaking about FEA, did you verify your solutions?
Yes, sir. We did do some convergence checks on everything that was shown. If whoever's controlling the PowerPoint can actually go to the FEA link, we can show an example of that.
That would be Ryan that's controlling.
I think it'll be previous FEA, and then scroll a little bit forward. That was actually done last semester, so if you want to keep going to show the models that we did this year, keep going. There it goes. So as you can see, we doubled the number of nodes and then did various convergence checks to see whether it was essentially converging at a value appropriately.
I have a question, Dr. Nick.
Hold on, I wasn't.
Sure.
I was talking and I was muted. Sorry.
Yeah.
No
So,
problem.
very good. You have the goods. Just as a point of consideration for the future, the audience may not know what you've done the previous semester or in a previous lifetime. So a simple statement that you did do verification and maybe some rudimentary information would give the audience more confidence that
Yes, sir.
what you're showing is valid. Do you have a free body diagram that will show the forces on the frame and also the forces on the parts that are supported on the frame?
Not on this PowerPoint, no.
That is something else that I think it would be good to have. And this is a comment, and then we have others that want to ask questions. I'll make this comment. What you're lacking is at least one slide that explains your product architecture. You know, what are all the parts that come together, an assembly drawing basically labeled so that people understand what you have in the entire product, and that should be up front. And now I'll give the floor to Fred Gillespie.
Good afternoon, team. I had up front, you said that you looked at 2 schools from last year, I think. Last year's competition, maybe?
Yes, sir.
Or a past competition. I think it was
2018.
MIT and somebody, I don't remember, but they had come in 4th and 5th place.
Yes, sir.
Was there a reason you didn't look at why versus number 1, 2, and 3?
Yes, sir. We shot for the top 5 positions because in these competitions, some of the teams are professionally sponsored.
Right.
And hundreds of thousands of dollars. So breaking into the top 5 is an accomplishment in itself when you take into consideration the professionally sponsored teams.
Yeah, that's what I recall from past years, but I thought that might have been the case. And also, I think you said somewhere, maybe I don't remember if it was top speed, acceleration, lap time, but you thought that you maybe based on your analysis, you could come in as much as 4th on one segment of the competition. Was predicted versus last year's results?
Correct. That was based off of the 2019 Lincoln's competition.
Right. But how you thought you're going to do this year, looking back at if you did that last year, how you'd place. Okay. I want to compliment you. And it's just probably my background as a project manager for large petrochemical complexes, engineer, design, build, test, commission. I want to compliment you on your showing predicted versus actuals for all your activities. Sometimes we get these simple bar charts for others, and you really don't know. They just know they did it on time. In other words, it wasn't slipping their end date. And also your little simple slide on project management issues, more communication or misunderstanding. I don't remember what they were. That's a plus also, because it's usually those type of issues that if you avoid those, you're more likely to maintain once through design and fabrication. But I want to compliment you on the project management slides in particular. I thought it was very good.
Thank you.
That's why you're on time probably too.
Right.
So appreciate it. Thank you.
Thank you.
All right, Gabriel.
Guys, I was a little bit surprised by you all's choice of the Arduino microcontroller. And I have been looking here. Looks like the program that it is running is not a very complex program, and is basically dealing with accumulating a lot of the results of some of those logic circuits that you guys created. So why didn't you create a specific circuit, in other words, a hardwired circuit to do what the program is doing, in the Arduino, and you chose to go with a program decode type solution?
So to answer that, so we do. So the brake plausibility device that Anne talked about, that is exactly that hardwire code, but those check for different things. So the Arduino essentially controlled all the small accessories. That's why we chose to go with a simple Arduino encode. So the only thing regarding that circuitry that the Arduino is checking is essentially 2 voltages. And if those voltages are within 10% of those, and if not, we submit a high fault to the BMS. So it really isn't analyzing a vast amount of data that we need a high clock speed for. So we just use an Arduino for that, as well as to control the 4 fans for the cooling.
Okay.
Right. And to piggyback off of
I
that,
got you.
I was going to say the BMS also has a completely separate microcontroller that does have a higher clock speed. So we
Yeah.
kind of covered
My worry was the low speed of the Arduino, and the functions that it was performing were not really that great, that most probably a circuit by itself would have done that. But like you said, it's controlling some of the fins, so it has the capability to control those in an easier form. I'm good. Thank you for the answer.
Thank you.
Thank you.
Right. I believe there are no more questions. Thank you very much. Give them a hand.
Thank you.
Thank you.
Guys.
We'll have a good one.
And have a good afternoon, Ryan. Thank you for releasing me.
Thank you.
And we will resume at 4 o'clock for the last presentation.